Hi everyone, hope you're doing good. Before we get started, just wanna point out that there's a new homework available on Mastering Physics on basically electric charge and electric field. So the chapter we just started this week. So, I mean, as usual, I strongly encourage you to get started as soon as possible to get some practice. And I want to really highlight that this chapter and probably, I mean, the few chapters coming on electric fields are going to be pretty calculus intensive. And this is going to be a lot of vector calculation and also some integration starting from today. So that's, I mean, that's not anything to be afraid of, but that's definitely something you need to practice. And, once you've done usual integration a few times, 3, 4 times in different exercise, you won't be as scary anymore. So really, I encourage you to practice. We'll do some example during class. You have some example to do as homeworks. And you probably do also some computation in discussion section. And I really encourage you to redo those examples, those calculations at home, so you can, have everything in mind. And then when you have a test or when you have to do it by yourself, it will be just a breeze. Okay. Then before starting, just a quick reminder, what to take home from yesterday. What's really important is Coulomb's law. So Coulomb's law is the law that dictates the force that results from the interaction between two charged particles or two charge unities. And basically what Coulomb's law is saying is that the force resulting from those is proportional to the product of both charges. And you see I've put those absolute value bar to remove the confusion from yesterday. So force is proportional to the product of those two charges and divided by the square of the radius, the distance between the two charges. And this force is along the line between the two particles. And then it's attractive if the sign of the two charge are opposite, and repulsive if the charge are same signs. Okay. So now today we're gonna introduce a new concept for this study in electricity, and it's the concept of electric fields, because we've established that charge interacts together through Coulomb's law, but yeah, and that's true even if there is just vacuum or an empty space between the two. The Coulomb's interaction doesn't need any medium to have an effect. But the question we can have is, how does Q2, for instance, how's this charge knows that Q1 is here? How can they interact if they're just in vacuum? And I mean, that's kind of the same problem for gravity is, how does the Earth, affect the moon from such a far distance? How do the moon knows that it has to be attracted to the Earth? And the the way we explain this is by saying that this charge, this electric charge, are actually dressed with what we call fields, which is a region of influence. And these fields are actually defined everywhere in space. So in the whole space, this charge has, this field of influence. And when another charge, where they're in this overall space, well, they can feel the field of the particle, and that's how they interact with it, because they locally interact with the field at this position. And so the force between the two particles comes with interaction of this particle with the field of this particle. And another thing to note is that this particle Q1, this charge, has a field, but it's not interacting with its own field. It's not it doesn't sense its own field. Same way as the Earth is not attracted by its own gravity. So it's the same from electric charge. And yeah, another thing is if you remove this particle here, this particle Q1 and its field are still there, because remember for the force we define the force as the force and using the charge of the two particles. But now, so to define a force, you need two particles, but the field is just associated with this particle and exists even if there's no other charge in the vicinity or in the system. So, uh, so that's why fields are pretty interesting to use as a concept, because then you can have a description more general, because it just depends on your charge or your charge system, and not on an outside test charge that you would use. And of course, this second charge Q2 also has a field of influence, and Q1 is sensing this field of influence and is interacting with Q2 through this field of influence. And now let's say we have another particle like a Q3, then Q3 will sense both the fields of Q1 and Q2. And what we'll do is we add the electric field from both particles to get the global fields. And Q3 will also have a field. So, you see how it's going to evolve, and you see that we'll end up summing all the fields from all the particles to get the global fields. Okay, so how to define this electric field? So we have, if we have an unknown charge Q here, and we have our test charge Q here, and when we put our test charge in the vicinity of this mystery charge, there's a force that arises on this test charge that we know the charge here. And this is the force F. And if you move this test charge kind of everywhere around this mystery charge, you can map out the electric field, because we define the electric field as the force that a particle of a test charge would experience divided by Q here, which is the charge of the test charge. And so we have the electric field that is 1 divided by 4 pi epsilon 0 multiplied by Q, which is the mystery charge, and the square radius. And why is it interesting to consider this and divide by Q, which is the other charge, the charge of the test charge, is because we have the electric field associated with this mystery charge, which only depends on the charge Q of this mystery charge. So we start from a force that depends on your test charge, and so you cannot define it for every particle. It's just very specific to this situation where you have your test charge, to something that's only specific to your charge you're trying to characterize, because it only depends on this large Q here. And So we see that yeah, E is the force divided by Q, and conversely, the force that a charge would a charge this test charge would feel is just the electric field multiplied by the charge of this particle here. Okay, so let's see how it looks for simple cases. So the electric field, so let's consider the electric field of a single positive point charge here, so plus here. And in green, we have the local value of the electric field. I mean, and so the arrow direction is the direction of the electric field, and the color scale is corresponds to the amplitude of this electric field. So white is high amplitude, and then bright green is intermediate, and then when it goes to darker colors, it's really dropping in amplitude. And so we see that the electric field is pointing outward for this charge and dropping in amplitude as we get away from the point charge. And this is coherent with the dependence in square of the distance here. And if you reverse the charge and you get a negative charge instead of positive charge, you'll get the same thing, just with the arrow pointing toward the positive charge. And so you see, the first thing you can see is that note is that for a positive charge, the electric field is pointing away from the charge. It's going from the positive charge and it's going out, and it will be the opposite for a negative charge. Okay. And in a similar way as we did for forces, we can apply the superposition principle and get the total electric field. If we have a collection of charged particle, if we have to get the total electric field from this collection of particles, we just sum all the contribution of the single charge or single elements. And again, similarly to the forces, uh, remember that these are vectors. And so if you're doing the sum, you're adding vectors, and you have to take into account the direction and not only the amplitude. And yes, and that's, as said earlier, the force, given a specific electric field, the force that a charge will feel in that field is its charge multiplied by the electric field. And then you see that the direction is determined both by the value of the electric field, if the electric field is positive or negative, but also the value of the charge, if the charge is positive and negative. And you see that this direction, depending on both sides of the charge and electric field, you will get a specific direction for the force. Okay. So you have a particle with a charge minus q. So this charge is negative, and it's traveling at a velocity v along this line here toward a region here where we have a uniform downward electric field. So the electric field is pointing, as shown here, down. So which is going to be the trajectory of this q, charge q minus q here once it enters the region of the electric field? Right. Okay, so the right answer is the number 1. And this can be understood if come back to this force is equal to the charge multiplied by E, by the electric field. And so here, since the charge is negative, we'll have the sign of the force will be opposite to the sign of the electric field. And so if the electric field is pointing down, the charge will go up because it's a negative charge. Okay. Now let's look at an example to get the electric field that result from the contribution of several different charge at a specific location. So we have this point P here that is at the edge of a square or a rectangle, I would say, from one side A and the other side B. So here we also have a B, and here we also have A. So we have 3 different charge of different charge value. Okay, so let's solve the value. Let's solve to retrieve the value of the electric field at this point P. So let's start by getting the contribution of the single contribution of this charge. So let's start with E1, which is the contribution of Q1. And so using the expression we've just established before, the charge from Q1 is 1 divided by 4 pi epsilon 0 Q what. So this is a general expression. So Q divided by the distance, and this force is along the the segment. So it's in this direction, or maybe in that direction, depending on the sign, but it's along this line here that we call R. And so so the charge here is Q1, and then we see that this distance R is the long axis of this rectangle triangle. And so we have that R square is just, R is equal to the square root of A square plus B square. And so R square is just A square plus B square. So this is E1, and it's along this R vector, unitary vector, so along this direction. Now, if we look at the contribution of the charge 2, so it's Q, so it's the same constant before, and then Q2 divided by this distance here, which is B square, and now the vector is different because it's now along this x-axis. And if we look at E3, now it's 1 over 4 pi epsilon 0, the charge, so Q3, and the distance, which is A square, A, and so divided by A square. And now the direction between the two is minus y, assuming y is going into the positive direction. And so now we have the 3 single contributions. We can add them together to get the total electric field at this point P. So let's do that. But before that, we need to, convert this cylindrical coordinate R into Cartesian coordinates. And so here we see that R is just cosinus theta x minus sinus theta y. And this you can just, trigonometric observation. Here, if you have R, here you have X, here you have y, and theta being the angle. Or you can also express it as a function of the sides of the triangle or the rectangle, because cosine theta is, if you have theta here, it's just going to be b divided by the value of the hypotenuse here. So a squared plus b squared and square root of that. And sinus theta now is just the value of the opposite side of the triangle divided by the long side of the triangle. So a divided by this term r here. And so now we got everything expressed as in Cartesian coordinates. So we can add all the contribution together. So we get the electric field is equal to, we can factorize this 1 divided by 4 pi epsilon 0. And then first, let's look at the x contribution. So we have, for the contribution of x, we have Q2 here, and we saw that the contribution was Q2 divided by b squared. And now we also have the contribution of this term here from Q1. And so we have Q1 multiplied by this distance, and so that gives the contribution in x, but there's also a contribution on y that is both from Q3 and part of Q1. And so for Q3, it's again pretty straightforward, just Q3 divided by the distance a square. And then this part, this term from the Q1 contribution, the vertical contribution of Q1. And so that we retrieve here. And so that gives us our total electric field here. And so you see that, as soon as we get a few charge and that they are not aligned and you have to take into account the geometry, you can get pretty tedious calculation. And right now, this was a pretty simple example where everything is along a rectangle with a right angle, but you can get into more complicated computation when you have a specific charge at a random position and you have to get the angles and you get some trigonometry and some calculation and change of coordinates to get from cylindrical to Cartesian coordinates. So yeah, if you have some time at some point, try to redo this one at home just to get familiar with this method. When we have a specific, a few specific charge and summing all of the contribution, taking into account the direction of the force. Okay, is that clear to you guys? What we did here? Okay. Okay, so similarly to what we've done in the fluid chapter, at some point to describe the flow, we were, studying and having flow lines that were tangent to the velocity of the flow. And so we can do the same thing to describe the electric field, having electric field lines that indicate the direction of the field at a specific position, and where the force acting on a positive charge would be tangent to this electric field here. So for instance, if you have an electric field that is curved here, you place your electric charge somewhere around here, and at this specific location, the force acting on this charge will be tangent here. And now if you put it here, the force will be tangent to this local area. So that way. And if you get a negative charge, they will experience now an acceleration opposite to the field lines, but still along the tangent. And if a field line starts on and field lines, typically, the rule is that they start on a plus charge and they end on minus charge. So there, if you have a plus charge and a minus charge, field lines are going from the plus to the minus. And if you have, for instance, only a plus charge, the field lines start from the plus charge and continue forever because there's no negative charge to end up on. Another thing is electric field lines never cross. And again, another similitude with the flow lines from the fluid chapter is that the separation between field lines indicates the strength of the field and how it evolves. So if you have closer field lines, it means that your field is getting stronger. And conversely, if your field lines are getting far apart, it means that your electric field is getting weaker. And so you can use that to estimate how your electric field evolves spatially. Okay, so here's a few example of charge distribution and their associated field lines. So I've drawn this, I've shown this positive, just a single point charge. Then you have the field lines like originating from this point charge and going, away radially. And now if you're considering a negative isolated charge, now you have the same radial distribution, but going toward the negative charge. Okay. If you get two, a combination of a plus and minus charge, which is what we call an electric dipole, then we have this distribution. And one thing that isn't interesting about the dipole is even though this is globally neutral, it has a field when you are outside of this dipole here, but it falls off pretty quickly with a dependency of 1 divided by r cube instead of the 1 divided by r square of the single point charge. If we have two positive charge, then the field lines look like this, and they don't connect because the field lines go from positive to negative, so they don't go to positive to another positive field, positive charge. And for what will be something that we will see later in this later in the summer is capacitors. And typically in capacitor, we have a line of positive charge and a line of negative charge. And what we get from those is straight field lines inside the capacitor. And then the fields drop very quickly outside, and it curves on the outside, and then almost no fields afterwards. Okay, so we have to charge A and B, and I'm not giving you the relative sign of those two charge. I'm not telling you which one is positive, which one negative, or if they are both positive or negative, and the amplitude. But what I give you is this electric field line pattern, and based on this pattern, what can you say on the sign and amplitude of those charges? All right. Yeah, mostly answered the choice number 2, which is correct indeed. we've seen that the field lines start from a positive charge and go to a negative charge. So yeah, this is indeed positive, negative, and then the amplitude of the two. We know that B is a stronger charge than A in amplitude because the field lines here are more tightly packed. So they are more close together, means that it has a higher charge because a higher electric field. And then A here, we see that they're more far apart, meaning that the charge is lower than B. Okay. So now we have a dipole here. With the typical field line distribution of a dipole, and we place an electron, so a negative charge here at point P. So in which direction it will be accelerated? Okay. Okay, you mostly answered number 3, which is correct. The charge will experience a force that is along the field line. So this is the case for both positive and negative. So in that case, no matter the charge, it will be along that field line. And then the question is it going in the direction of the field line, so down or up? And uh, and to look at that, just look at the sign. And since it's negative, it's going in the opposite direction of the field lines. And therefore, it's going up. Okay. And the last example to make sure we understand this. So we have an electron placed at point P here. So in which direction would be accelerated? Okay. So yeah, this time, it's still an electron, so it's still going in the opposite direction of the field lines, but now we see that this is a positive charge here, and the field lines are therefore oriented outside, going out in the outward direction. And so in that case, the electron is going to be going inward, because the electric field is pointing outward. Okay, and here you see so here you see the electric field represent for three different configurations. So here we have the monopole, which is just a fancy name for a single particle, isolated particle. So here a plus charge, and the distance dependency is of the electric field is in 1 over r square. Now, when we have a dipole, we see that this field drops much quicker. Here you see that the light green, for instance, is dropping relatively slowly. But for the dipole case, we see that we drop pretty quickly into the dark green region, which is lower field. And this is because it drops in 1/r³. And now if we consider the quadrupole case, where we have not 2, but 4 charges. So it's still neutral overall, but it still has some charge that gets, still some electric field associated with this distribution, but now the drop is even more abrupt. And this configuration has an electric field that evolves in 1/r⁴. So really, really, really close, really for fast drop of with the distance here. So yeah, so we've seen that the electric field, of a single particle, 1.6, yeah. So yeah, the equation we learn for the electric field is the electric field associated with a single charge particle. And then, everything else you'll be facing, in this course will be just a more complex variation of that, because everything is made, if you have a dipole, it's made of 2 monopole or two single charge. And so if you want to get the electric field of the dipole, you can just sum the 2 contribution of the 2 charges at, for all the position, and then you get the value for the dipole. And if you have 4 charges, you just do the same thing at the contribution of single charges, and you get the contribution of this system. And so, yeah, this expression is, it's only for one charge, but can be applied in basically all the situation, because everything is made of a collection of charge, a collection of single charge that brings the system to complexity. And yeah, that gives me a good segue to this slide, where, if you want to get the total electric field for any charge, and we use the principle of superposition, and so you just sum all the contribution, and has magnitude and direction. But now let's say that, instead of having 5, 6 charge, we're gonna have, as in real life, just a massive amount of charge that are very close together, and we're starting to get toward a situation where it's more like continuous, even though it's made of tiny integer parts of charge. It's not charge are still in chunks of at least an electron, which is the minimum charge. So it's not perfectly continuous, but if it's small enough, and if you have a large amount of them, you still are evolving toward a continuous, some kind of continuity. So here, if you get very large and continuous sum, then you start getting toward integral, where you have instead of having a sum, if you're summing into a massive amount or an infinite amount of small chunks of charge, then you're not doing sums anymore, you're doing integrals. And that's why this chapter and the rest of the electricity chapter are going to require some calculus, because to get electric field, and we'll have to do some integral calculation. Okay, and so yeah, when we are going to consider cases where we don't really have like very defined specific a very defined collection of a few charges, but charge distribution that we will consider that are continuous uh, and just uniformly reparted. So for instance, we can have a line of charge, and in that case, we just use this linear charge lambda, which is, I guess, the total charge divided by the distance. So it's the charge per distance. But we can also consider cases where we'll have the charge, the overall charge on a surface, and considering this surface as just continuously charged with a small amount of uniformly reparted charge. And so therefore here this surface charge we would call sigma, and would be in Coulomb divided by square meter. And of course the more general case would be if we have charges reparted in a volume. So now we have this charge density rho, and it would be in Coulomb per cubic meter. And so, I mean, these three can represent the same thing, just depending on the geometry that's changing. If we are doing 1D, 1D collection of charge is gonna be, we call it lambda. If it's 2D collection of charge, we call it sigma. And if it's a 3D distribution of charge, we call it rho. But it's always charge density, just the dimension is changing between the three. And so when we're considering charge distribution, we will follow a specific strategy to compute the fields for those complex distribution. So first, for every physics problem, it's always a good idea to make a drawing of the distribution and having a coordinate axis and then indicates the position at which you want to calculate the electric field. And then we will have to do something that is specific to calculus and integral calculation. Is we have to define a small element of charge that we can consider as almost a point charge, and that will have to have some infinitesimal length or volume of dx, dy, dz in Cartesian coordinates, or if we are in cylindrical coordinate, it can be gr d theta. But yeah, we have to define a small element that is general to the object. And this small element will also have a small charge q. And this dq, when integrated over the whole object, will have the total charge, large Q. And so once we have this small charge element from the system, we can define the electric field E at a point P that is caused by this small element of charge dq. And so now we have the dE, the small contribution of the electric field from a small element of charge dq. And so to get the total electric field E, we just integrate over all the dE on the system here. And so we just integrate this small contribution of the to the electric field for the small element over the whole system. Sometimes, the symmetry that can help us reduce the complexity of the problem if possible, because we can have a situation where some asymmetry will make some contribution disappear, and if you just observe it right away, you don't have to do the calculation to figure out this this part disappears. And make sure that your integral limits are correct. They correspond to your system and they have the correct units. And then once you get your final result, you can check that your electric field makes sense. I don't know, let's say that your charge is positive, make sure that, oh yeah, the direction is in the right, oriented, yeah, makes sense considering this is a positive charge and stuff like that. Okay, so to make things more clear, let's do an example together and apply this method. So this is an example from your book, from the textbook. So you can, if you want to redo it, you can use the slides. You can go check how it's done in the textbook. I mean, I'm using a very similar, it's basically the same derivation, I think. But yeah. So we are trying to get the electric field caused by a charge line segment here. So this is just a line that has a total charge Q. So the total charge of the line is Q, and it has a length 2a. So this is the origin, and it spans from -a to 2a. So yeah, and so first we can define, the lambda with for a line distribution. So here it would be, we have Q, this is the total charge, and divided by the length. So here the length is 2a. So we can remember that the lambda is Q divided by 2a, and we'll use that. So now we want to get the electric field at any position along the x-axis, at the origin, at the center of this segment. So let's place a point P at a distance x from this line. And so and then we consider a small charge element from the segment here. And so that is represented here. So this small element have a small charge dq and a small height dy. And this small charge element is, it's charged, so it's creating a small electric field at this point P that is along the distance, along the line that connect the two. So we have this line along the R here, and so the electric field is just dE. The small electric field that we call dE is along this line here. And so for the distances, we have the distance in x, from the distance P from the origin is x. The distance of this element dy is y from the origin, and therefore the distance of this the distance from this small element dy to P. Sorry. So yeah, the element from P from the small element dy is r equal x squared plus y squared to the power 1/2. So the square root of the two sides of the triangle. Okay, so here we have the system defined. So let's first let's get started by getting the value of the small charge, the small electric field created by this small charge, so dE. So using so it's a small element, so we can consider it's a point charge. And so we can apply the small electric field. We can apply this electric field for the electric field formula for a point charge that we learned. So this is 1 divided by 4 pi epsilon 0 multiplied by the charge, so dq, divided by the distance, so r square. And this is along this. So r here is the unitary vector along the r direction. And so dq here can be expressed as as a function of dy. It's just the total charge. It's just the charge per unit of length, so lambda. So q, and lambda is q divided by 2a. So we have q divided by 2a multiplied by dy. And so dq is just the small charge of that, and the small charge is just the charge per unit of length multiplied by the length of this element, and this length is dy. And so we have the total small contribution for these elements is expressed here, but it is expressed in cylindrical coordinates r, and so we want this to be as a function of x and y. And so we observe that we have, if we have alpha yes, okay, it's there. And so we want the contribution in Cartesian coordinates, so basically ex and ey. And so using this drawing, we can see that the small element along x is just dE multiplied by cosinus alpha, and alpha being this angle that we retrieve also here. And similarly for EY, we have that dEy is just the total dE multiplied by the sinus alpha here. Okay. And so if we get, so let's start with the x contribution. So we just, use this one that we retrieve there. It's also there. And then there's the cosinus alpha here. Okay, and just trigonometric relation gives us that cosinus alpha can be just x divided by r, because cosinus alpha is gonna be this side divided by the long side of the triangle. And so we obtain this expression for the small contribution of these small elements along x. And we get 1 divided by 4 pi epsilon 0 multiplied by q divided by 2a r square x divided by r. So we have a r cube here. And by applying just this relation where just substituting r by its expression as a function of x and y, we obtain the final expression for the contribution along x of this small element of charge dq. And if we do the same thing for ey, we just get the same thing, just as the difference that we had a sinus alpha, and sinus alpha can now be its opposite side divided by long side of the triangle, so y divided by r, and that gives you this expression for ey of the elements. Okay. So now we have the contribution in both directions, so x and y for this small element of charge dq. And so to get the total contribution, so the total electric field at a point P, we just integrate over the whole segment. We integrate those contributions over the whole segment. And so this gives us, so this term is constant, so it can go out of the integral. And then we integrate between minus a and plus a, because that's the length of our segment. And we integrate this term as a function of y, because we're integrating along the the vertical segment. And I'm not gonna go into the details because actually solving this integral is pretty complicated. It requires to do not so easy substitution by writing y, the substitution y equal x tangent theta. So if you want to do it at home, have fun. It's otherwise you can find the solution online for this equation, for this solving of this integral. It's not something I will require you to do. We'll do some integral where that are more easy to that are easier to solve, and you will be able to do it in class. But this one is a bit too complicated, so I'm just gonna give the final answer, and so integrating this between minus a and plus a, we obtain q divided by 4 pi epsilon 0 multiplied by 1 over x multiplied by x squared plus a squared to the power 1/2. So yeah, this is the contribution, the electric field along x for a point P along the axis. And then we see that we have a general, expression along x. So this is valid for any x position along the x-axis. And now we can do the same thing for EY. So for EY, we just integrate over this small contribution of the electric field along y. And if we do that, we notice that we have an asymmetric function. So here we have y squared, so this is symmetric, but here we have y, and y is by nature asymmetric function. And so we have asymmetric over symmetric function, and that gives you an asymmetric function, meaning that it's if you go to the negative value, it's the opposite of the positive value. And therefore, you don't have to calculate this integral and just get 0 because the negative part is exactly compensating the positive part. But could we have guessed it that this contribution was 0 without any calculation? Yes, if we apply, our point number 6 before doing any calculation. So let's look at symmetries. And yeah, it's pretty obvious that this system here is symmetric along the x-axis, and we have as much charge on this side than on this side. And therefore, when we are on axis, it's just, this electric field caused by this side is just compensating this one along y, and therefore there is no electric field along y. So always keep an eye on symmetries. It can gain you a lot of time by just trying to skip a complicated computation or integral calculation, because you can just see directly that there is a symmetry in your charge distribution. Okay, and so this gives us our final answer. So we have the total electric field on axis that is equal to this expression. So 2a lambda divided by x multiplied by square root of x squared plus a squared, or if we just either depending on what you want to do, you can express it as a function of the total charge, or depending on what the problem is giving you, either total charge or just the linear charge and the size of the object 2a. So just because q is equal to 2a lambda, or lambda equal q sur 2 over 2a. Okay, and now we can see how this expression evolves if we're considering the case where either A, so either this segment is extremely long, so almost is infinitely long, or the case where we are extremely close to the segments. And I mean, they're kind of equivalent. So if a tends to infinity, or x is negligible, very small compared to a, then we have this term become negligible compared to this one. And so we have a that comes out, simplifies, and you just get a dependency in lambda divided by, in 1/x. And so the electric field decrease as a function of 1/x when you get away from if this line is infinitely long. Okay, so this is a typical reasoning you would have to do. I strongly encourage you to do it, especially, one of the most fundamental steps to do is, determining your small, charge element and its contribution to the point P, and then looking at how it simplifies, or how you can express it in your coordinate system. And then it's just some calculus to do. But, once you get to the calculus part, it's just, you've done the most important part of the reasoning. Is just defining your system and getting your, estimating the contribution, and then it's just some calculus to do. Okay, so another example, we're not gonna do it in details, but it is this charge ring example. It is in your homework on mastering physics. It's also, it's also done in the textbook. I think it's done step by step in the textbook. So I strongly advise you to do it thoroughly. Follow it step by step in the textbook. Do your homework on that. And it's a similar way where you define your charge element dq. You have a point P on axis here, and you get the small contribution of charge associated with this small element, small contribution of electric field associated with this small charge, and then you integrate over the whole ring. And if you do that, I give you the general result. You get this expression of the electric field. Which is relatively complex. Now you have x, we have an x there, and a dependency 3/2 at the bottom for this x squared plus a squared. And if we do the same reasoning, where if we consider, but now we consider to be very far from the ring. So we have a ring, and we consider that we are, at a position very far compared to the side of the ring, so to a x very large compared to a. We see that this simplifies. Basically, this goes, and then you have x squared power 3/2, and so x up to the power 3, and with a x at the top, just simplify and get x squared. And we get this expression. This is pretty interesting because I don't know if it rings a bell to you, but it's exactly the expression of the electric field caused by a point charge. And so basically what this tells you is that this ring here, a ring of charge, if you're sufficiently far away, it just behaves like a single point charge at the point O. So this is interesting to remark. Okay, so if we have a circular ring of uniform charge, as we just look at the the contribution on the XY axis here, and we look at the electric field along Z, which graph would accurately represent this situation? All right. So the right answer is the answer number 2, because the first thing to notice is, in this expression, if x equals 0, then this is equal to 0, E equal to 0. So the electric field has to be 0 on axis. And then if the ring is charged, no, if the ring is as a specific charge, then when you go into one direction, it will have an effect on you. So let's say it's gonna push you into that direction if you're a positive charge and the ring is positively charged. And so if you go into the other direction, the ring is still positively charged, and so it's natural that it will still push you away. We have the same effect, and so the electric field is on the other direction. It's pointing toward the other direction. And so that's why the electric field is the other sign. It's because it has to stay consistent with the charge of the ring. Okay, so these first two examples, so the segment that we did together and the ring that I asked you to do as a homework. So these were examples in 1D, so 1D distribution of charge. But as I've said, we can also look at 2D distribution of charge, and for instance, a uniform disk of charge. So this uniform disk has a total charge Q, and this time, we still have to define a small charge element, which is an infinitely small element that has a small charge and that will be integrating over. In that case, for a circular element, the smart thing to do is to take an element that is just a small ring of a very small size, of a small transverse size, and that has a radius r. So this small ring has a radius r, and this radius can be will vary during the integration, and it has a small width dr. And so this is because this dr is very small, that the total charge in this small ring is also very small. Okay, and so since we're considering uniform disk now in 2D, we get the sigma, which is the charge, so the charge dq divided by the area dA. And here, the small dA of this small ring of width dr is going to be, so this area of this ring is going to be 2pr, so the radius here. So 2pr is going to be the circumference of this ring. And so if we multiply the circumference with the width dr, we get the area of this small disk. or of this small ring. Okay, and now we can estimate the small electric field caused by this small element of charge dq. And so the small element, the small element is 1/4 pi epsilon 0 and multiplied by the charge. So this is dq. And wait, yeah, no, this is yes. What we're using actually is this electric film from a charge ring here, and we've estimated this. We've shown that it was equal to this, and now instead of having this large Q, we're just using a small dq. The small dq here is the 2 pi r dr multiplied by sigma. So this is the dq, and x is the distance that was already in the expression of the E that we got that you're gonna compute to get the value of the ring, the electric field from the ring. So this uses the value we got from the ring before, and then we can just integrate to the sum of all the small contribution of the small rings using a radius starting from 0 to r large R, which is the radius of the disk. And so we do that, we can get the constant terms out of the integral. And then we have the integral of between 0 and r of 2r dr over x squared plus r squared power 3 half. And this time, we can do the computation. It still uses a substitution, but a simpler one. And so we can write, the substitution, we write t equal x squared plus r squared. And so that also gives can get the differential elements dt by differentiating this, and this just gives 2r dr. And so, yeah, and that gives the final integral that is, this term. So call k for the constant, and just give an integral from x squared to x squared plus r squared, the dt over 3 over 2. All right. So this, this substitution simplify this term to this one. And this is, we know primitive for this integral, so it's easy to integrate. And so if we do that, the primitive of this previous equation of the previous integral is just minus 2 t to the power minus 1/2, and evaluating this at the two limits of the integral gives. So we evaluate this for x and x square, x square and x square plus r square. So this gives us this term. And then simplifying, we obtain multiplying by x on both sides by x, we obtain this term here. And so we got the contribution for the whole disk. And now we see that, we can again apply the case, the reasoning where we consider that the disk is very large. And for instance, if we consider a disk that is infinitely large, that it becomes, just a fully charged, a fully charged plane. We take R very large compared to X. This simplifies, and this becomes very big, and so this tends towards 0. It just leaves the 1 here, and so we just get an interesting result that if we have an infinite sheet of charge, because if this disk is infinitely large, it just gets a sheet, then we just get a constant electric field, sigma divided by 2 epsilon 0, that doesn't depend on the distance to the sheet. Okay. And so that gives us those, to summarize, if we have a point charge that's, from Coulomb's law, we get a dependency of the electric field that varies as 1 over r square. If we get an infinitely long line of charge, we get a dependency that is in 1 over the radius rho. And if we have an infinite sheet of charge in 2D, then we have an electric field that is independent of the distance from the sheet. And this is interesting. Okay, yeah, guess we don't have a lot of, it's almost done. So just go over this final quiz. We're just looking at the answer. So we have a charge distribution. So which of these charge distribution will have an electric field that is varying as a charge divided by z square on the z-axis? And could be the first one, where we have a single point here. The second one, where we have a quadrupole and 3 different charges. Here we see 2 lines, charge minus and plus, infinitely long, and then a ball of charge 2q on one side and minus q on the other side. And so in that case, the right answer would be the number 4, because if we place sufficiently far away, what you get is if it's symmetric like that, to get to have something that depends on q here, the overall charge has to be q, And that's not the case here. And so that's why, because when you go far away, sufficiently far away, this one looks, I mean, those distribution looks like a single point. And so you can apply the Coulomb, the typical distribution, the electric field formula for a single point. Okay. So that's it for today. I strongly encourage you to go back to these examples because, I mean, that's the kind of thing that if you don't do it by yourself, you won't really grasp, feel like you understand, but when you have to do it and try to do it yourself, you see, the details of it, what you don't understand, what you understand, and if you want, we can, discuss it tomorrow, if you are during office hours and see if there's some point you don't understand in the derivation. But you will, at some point, either in the final or some point, or for as a homework, you will have to do some integration calculus. And so be ready for that. All right. Do you have any question on that? Otherwise, I'll see you tomorrow.